A torus meets an equation, and it turns out they're made for each other. Intuitively, a torus is the surface of a donut. It's a fun shape to play with, especially if you pretend it's made out of really squishy rubber. This video series is about taking a rigorous approach to a torus by parametrizing it, and then exploring the behavior of vector fields on this delicious surface. You can describe a torus mathematically in many different ways. You can think of it as a subset of R3, all the points in space whose xyz coordinates make a certain equation true. At first glance, the equation might look like nonsense, though, so let's think about how else we could describe a torus in space. A torus is a bit like an inflated inner tube, so maybe we can imagine starting with a deflated one, and just lying it down on the xy plane to make a nice, neat circle, maybe one of radius 2, so we'll have room to work. Then let's imagine pumping up the inner tube, making it thicker and thicker, until we've made it 2 units thick. In other words, the cross-sections of this pumped-up inner tube are circles of radius 1. Our torus isn't lying neatly on the xy plane anymore. It's spilling down below it, puffing up above it. The parts farthest from the hole are distance 3 from the origin, and the parts closest to the hole are distance 1 from the origin. But if we want, we could imagine that original deflated inner tube is still there, hidden inside this hollow torus, still lying in a nice, neat circle of radius 2. Let's imagine this circle in red so we can keep better track of it. So, if I picked a random point in space and told you its xyz coordinates, how could you figure out whether that point was on the torus or not? Pause the video and think about it for a moment if you like. What you could do is ask, how far is that point from the red circle? If the distance is 1, then congratulations, you've found a point on the torus. If the distance is any number besides 1, then this point is not on the torus. Better luck next time. So now we need a way of figuring out how far some random point is from our red circle. Let's look at this in 2 parts. First the vertical distance, and then the horizontal distance. Vertical distance isn't so hard. The circle's lying in the xy plane. So by vertical distance, I just mean how far does the point have to rise or fall to land in the xy plane? So the answer is just the absolute value of its z-coordinate. So vertical distance found. Moving on to horizontal distance. Once the point has landed in the xy plane, how far does it have to move to get to the circle? Let's look at how far the point is from the origin now that it's landed. We can call this number d, but it's just the square root of x squared plus y squared. Pythagorean theorem. If d is less than 2, then the point has landed inside the circle, and its best bet is to move straight away from the origin, traveling a distance of 2 minus d to arrive at its destination. If d is greater than 2, then the point has landed outside the circle, and it has to trek in towards the origin, a distance of d minus 2. Fortunately, the square of 2 minus d is the same as the square of d minus 2, so that gives us that h squared is d minus 2 squared. Now that we have the squares of the horizontal distance h and the vertical distance v, we can find the distance the point has to take to get to the circle if it flies there in a straight line. It's the square root of h squared plus v squared. Substitute what we know for v squared and h squared, and we get that the distance to the circle is the square root of d minus 2 squared plus z squared. And since we know what d is, we can substitute that in as well, and get the square root of x squared plus y squared minus 2 all squared plus z squared, and then take the square root of the whole thing. Finally, we've constructed it, a machine for measuring distance from a point to the red circle. And now we can define our torus. It's the set of all points in space such that, when you feed them into this machine, you get 1 as the answer. So this is our equation. We might as well square both sides to make it simpler. It might look like a jumble of symbols, but it's really a torus detection device, locating every point on that wily surface once and for all.